Assalamu alaikum. I'm Abdallah Faisal Ayub, roll number 23I6058 from Fast Nooses Islamabad. And I'm the team lead for our digital logic design project titled Binary Calculator. I collaborated with my teammates Zargam Ali, roll number 23I6083, and Muhammad Talha Sumro, roll number 23I6082. This project was part of our digital logic design course, and it allowed us to explore the foundations of digital arithmetic by building a calculator that operates using nothing but logic gates. Our calculator performs four basic operations on 4-bit binary numbers. We strictly use logic gates to implement each component from scratch, without relying on built-in arithmetic blocks or microcontrollers. The goal was to practically demonstrate how computation takes place at the lowest hardware level.
Our main objective was to construct a binary arithmetic system purely from elementary logic gates like AND, OR, XOR, NOT, NAND, and NOR. The project focused on performing 4-bit operations through a modular approach, where each arithmetic operation is handled through a well-defined logic circuit. We emphasized efficiency and scalability into our design. We also wanted to simulate the entire circuit in Proteus to validate our logic before physical implementation. The project required us to take theoretical concepts like binary addition, two's complement, subtraction, and logic minimization using Karnaugh maps and apply them to an actual hardware-oriented problem. This bridge between theory and real-world implementation was the most valuable learning experience for us.
Architecture includes multiple interconnected modules. The core components are the 4-bit adder/subtractor, a control-based multiplexer for operation selection, and custom-designed logic blocks for multiplication. Each module was designed to operate independently and then integrated for full functionality. The adder/subtractor module uses full adder logic with XOR gates to support conditional subtraction with 2's complement logic. We manually derive the logic for each bit addition, taking carry in and carry out propagation into account to ensure arithmetic correctness. For subtraction, we implemented inversion and addition of 1 to follow 2's complements rules. While it's a relatively resource-intensive process, we optimized it using simplification techniques to reduce redundancy. We placed great emphasis on logic minimization to reduce gate count, which we achieved using Karnaugh maps for all outputs. This helped us reduce delay, complexity, and potential errors. All logic expressions were tested independently before being integrated into the full circuit.
We have the inputs currently set to 0 and 0. We will now change one of the inputs, that's B0, to 1, which gives us the output for the first LED, which is indicating an output of 1. Now we'll change the output for for A1 from 0 to 1, which turns on the second LED. And if we try to invert this by subtraction, then we get an output of 0.
We faced two major challenges during this project. The first was reducing the gate count for complex operations like multiplication and subtraction. We tackled this by using Karnaugh maps and Boolean algebra to minimize the logic wherever possible. This reduced both physical complexity and potential sources of error. The second challenge was ensuring consistency and accuracy across modules. Since each arithmetic operation has different integral logic and timing, integrating them without introducing glitches was really difficult. We solved this by thoroughly testing each module in isolation in Proteus before integration. Additionally, we designed control logic to prevent multiple operations from activating simultaneously.
This project taught us how arithmetic operations are actually implemented at the gate level, deepening our understanding of how digital systems perform basic math. From creating full adders to constructing multipliers from logic gates, we now understand the significance of logic design in real-world digital devices. More importantly, this project emphasized the value of planning, testing, and teamwork in hardware design. From every error taught us something new, and every successful test made our design stronger. Overall, we've grown as problem solvers and engineers. Thank you so much.